registering in for this workshop and also for attending today. Uh, so in the morning session now, I will hand over uh, my control to Suresh sir. So he's going to talk about, he will be doing the inauguration part. So I request all of you to kindly mute yourself so that it won't be disturbing other people. So until and it is necessary, please don't unmute. So all of you, please mute your all your microphones. So, Suresh, to give the introduction.
Dear friends, myself, Dr. H.M. Suresh, Professor and Head, Department of Physics. All of you, and hearty greetings to one and all from Siddhartha Institute of Technology. At the outset, I submit my humble and devotional pronouns at the lotus feet of His Holiness Dr. Sri Sri Shivkumar Swamigalu and Sri Sri Siddhalinga Swamigalu, and seeking their blessings for conducting 4 days international workshop on X-ray diffraction analysis. As Rabindra said, candle cannot glow another candle unless it burns. I'll repeat. Candle cannot glow another candle unless it burns itself. Same way, researcher cannot do the research or think about innovation unless he learns or unless he updates the knowledge. In this regard, the Department of Physics is conducting hands-on training on X-ray diffraction analysis for the academician, researchers, and students. Dear participants, as you know that enormous research is going on searching for new materials with potential applications in various fields. But identifying the structure of the synthesized material is crucial before subjecting the material for its application oriented testing. And it is known that the presence of one or more impurities in the materials will have adverse effects on expected properties. The XRD is still first choice of characterization in material science research even after 100 years of its usage. This workshop will provide you all to learn phase analysis, refinement, microstrain analysis using open source software such as dear participants. Siddhartha Technology is run by Sri Siddhaganga Educational Society headed by Sri Siddhalinga Swamiji. SIT was established in the year 1963 under the blessing of Sri Sri Shivkumara Swamigalu, which is one among the 125 institutions run by Sri Siddhaganga Mutt. UGC, Government of Karnataka, and Vishweshwaraya Technological University Belagavi have granted autonomous status to our institute for the academic year 2007 and 8. The institute has been accredited by NAC with A grade. The institute is consistently ranked among the top 100 engineering institutes in the country for the fifth time in a row from 2016 to 2020 at the All India level under engineering category in National Institutional Ranking Framework, that is NIRF, MHRD Government of India. The Department of Physics is an integral part its inception in 1963 and is supporting all branches of engineering. At present, department has six faculty members, out of which 5 are with doctoral degree. Faculties have obtained funded projects from VGST, Government of Karnataka, DST, Government of India, etc. The Department of Physics is recognized as research center by Vishveshwaraya Technological University Belgavi since 2005. So far, 6 doctoral students have graduated and 12 research scholars are pursuing their PhD who are all registered under VT. It is my pleasure to remember our management, our director, Dr. M.N. Chamasapa sir, our CEO, Shukumaraya sir, and our principal, K.P. Shivananda, who have encouraged and supported to establish the 2 research labs with basic facilities such as UV visible spectrophotometer with integrated sphere attachment for DRS studies, LCR meter with temperature controller, glow box for assembling, manipulating battery materials and air-sensitive samples, UTM testing machine, the electronic workstation, high temperature muffle furnace and tubular furnace, etc. Beside to these instruments in the physics department, the chemistry department has powder XRD, FTR spectrometer, electrochemical workstation, spectrophotometer, atomic absorption spectrophotometer, battery testing unit, HPLC, thin film deposition units. And also the institute has some sophisticated instruments like tabletop SEM IDAX, micro hardness and tensile strength tester, ICP-MS, TOC analyzer in the chemical engineering department. So these are the facilities which are available in the institute to carry out the research work. So all these instruments are procured with the support of the management. Happy to share with you all that the scholars not only from the different parts of our country, but also from other countries like UK, USA, Saudi Arabia, Iran, Muscat, Oman, Mecca, and Madin, and other countries. Totally more than 100 scholars are participating in this work. Happy and appreciate all the participants for showing their keen interest on this workshop. I hope this workshop will fulfill your expectation. Before I conclude, I pray the God Almighty to keep all of us with good health from this COVID-19 pandemic situation. Be happy, stay safe, and enjoy this workshop. Thank you, one and all. Now I request Dr. Sridhar P. Munilmani to introduce the convener and speaker of this workshop. Over to Dr. Sridhar.
Good morning, everyone. I'm happy to introduce today's resource person and today's speaker, Dr. Madhu Chennabasappa. He has completed his bachelor's and master's from Mysore University, and later he joined Professor A. Sundaresh Jawaharlal Nehru Scientific Center for Advanced Scientific Research, and later he did his PhD under Professor Bernard and Oliver of ICMCB University of Bordeaux, France, and also he has postdoctoral experience from France and USA. He has been a recipient of seed money to young scientists for research, grant by VGST, Government of Karnataka, early career research award from SERB, DST, Government of India. He has 2 US and European patent on his name related to lithium-ion batteries, and 20 research articles in highly reputed journals like Royal Society of Chemistry, American Chemical Society, Elsevier, and IOP. He received several national and international awards, and he's the he is having expertise in lithium ion batteries and these Rich-Willed refinement. So this is the brief introduction of Dr. Sappa. Thank you.
Okay, so Sridhar and also our HOD Dr. Suresh Kumar for kind introduction and also for inauguration session. So now we will go back to our we will start our main session. So so I request all the participants to kindly mute your phones so that you don't disturb our uh, conversation. Okay. So to start with, as Sir has already given a very brief introduction about our institute, so I am not going to repeat those things. So what I will tell in the next 10 minutes is or so is because I think most of the participants is going to they are going to uh, join at 10 o'clock. So some of them wants to skip the introduction or inaugural. So uh, in this workshop, as you can already see, uh, program that is already shared with you. So I'll just open the schedule again. Okay, so this is our proposed schedule. So as I am the only person, I may slightly divert from all these things, but still we will try to cover all the things which are already given. Okay, so if you have any difficulties in either joining the meeting or anything, you always you feel free to contact us, and also try not to put any post like good morning and all those things in the chat. So let us keep the chat only mostly for our question and answer. Okay. So this is what I want to ask you. So beyond that, so I in the morning session today we are going to go. I will give more on the to the X-ray diffraction. So if you are already familiar with X-ray diffraction, it's fine. But still, there are some more participants who be uh, uh, beginners for this X-ray diffraction. So we will have to take care. We have to take care of them. So that is the reason I'm giving introduction. So in this part, I also will cover the detail data acquisition. So some of the errors that you need to avoid when you collect the data. So that is more important to do a really good analysis. So that is which we will cover here. So in the next session, so only for today, we are having 30 minutes extra. So that is mainly because we have to our inaugural session. So from 9:30 to 10 was the inaugural session. So anyhow, from tomorrow we will start. Then it will be having 1.5 hour session. So each session we will try to cover whatever is already proposed. Okay. Then half hour we'll take a 30 minutes break. So 9:30 to 11 is the first session. Then after 30 minutes from 11:30 to maybe 1 will be your next second session. Okay. So this will be there for your day 2, day 3, and day 4. This will be common for all the days. So only today we will have some extra 30 minutes. So in meanwhile, what I have planned is we will also have some quiz and assignments. So on the topics that has been covered. Okay. So in first 2 days we are going to cover some topics. Then you will get quiz and quiz 1 and quiz 2 in your email. So you need to just it will be multiple choice session questions. So you need to uh, answer them online. So it is then also will give assignment. Assignment in the sense it will be just to make sure you practice something during the workshop. So I will give you some assignments based on what we did. So I may ask you to do some phase identification, or I may ask you to find some slide size or strain of the some sample. Okay. So I'm going to send you the data, and then you need to do that. So that will be like that is the main thing. It will be a hands-on training. It's not just like we come sit here and we see the some videos. Okay. So it's more of we will have hands-on training, and if you have any doubt, you are always welcome to email me. So even if you get stuck in something doing something, then you can always email me. We will have the I will give you the solutions. Okay. At the same time, so we are having session only in the morning. The reason is in the afternoon you can do the practice. So all the sessions, whatever we are going to cover, it will be recorded, and then you give us time because uh, uh, we are recording on WebEx, and then we need to get those recordings from the cloud. So it will take some time. Once we get those videos, we are going to share those videos with you, so that you can have reference material to do your assignment and quiz. Okay. So this is how we will have. So the same thing will continue on the day 3 and day 4. So day 3 and day 4 mostly we are going to cover more on the ritual refinement. So in even in ritual refinement, different parts like indexing, or even just solving a crystal structure. Okay, to get your bond angle, bond distance, and all those. So these we are going to study on day 3 and day 4. And even when it comes to ritual refinement, it can be either on single phase or multi. So if it is a multi-phase, then you need to learn how to do the quantification. Quantification is in the sense the distribution, weight percent distribution of each phases. Those things you are going to learn on the day 3 and day 4. So again the same schedule, like you'll have 2 sessions in the morning. You have to do the you have to do or you have to try and
Class.
practice those things. Okay, in the afternoon. So this is the main schedule for our program. So for this, I think we can our first session for our today's talk. Okay, so so I'm going to switch to the PowerPoint. So so this first session is mainly the introduction to X-ray diffraction analysis. So the main reason is again there may be some participants who may be new to this subject, and so that is the reason why we are having this. So before I start, so I just want to remember our Reverend Swamiji, Sri Shivakumar Swamiji. He is a big inspiration in terms of the work he has done for uh, weaker section of the society. So he he is a founder president of our SIT, Siddhganga Institute of Technology. So he is also running Siddhganga Mutt, and there we have some schools like starting from primary to high school, and around 10,000 students from different parts of the state are getting free education. Free education in the sense free boarding, free food, and also education is free. So around every year you'll have almost around 10,000 students who are learning there, and they come from all parts of Karnataka, and also irrespective of religion, caste, and all. So this is just brief, very brief biodata of our Swamiji. So he was born in 1st April 1907, So he just left us last year, this year in the January 21st. So at the age of 111 years. So out of this 111 years, more than 85 years he has spent uh, looking after and also taking care of the children from different uh, just so kindly please unmute. Uh, So, he has got some recognition also from government, like Padma Bhushan from Government of India in 2015, and Karnataka Ratna, which is the highest civilian award from Karnataka government. So, and also yesterday was the birthday of our I think most of our favorite APJ Abdul Kalam. So, let us wish belated happy birthday to our missile man of India. These two peoples are something common, which is nothing but they had a lot of affinity towards children, because children are the next future, and all most of their work is based on to motivate these children. So let us start with this positive note for our workshop. So this is a very brief introduction about our Sri Shivkumar Swamiji. So let us come back into our so coming back to workshop. So normally this would be the last slide of any given workshop. So in principle, I am putting this as a first slide of the workshop. The main reason is, it was already mentioned in the brochure and all the things. So in this workshop, we are going to use open sources. So the reason is this should be like this should help in a lot of researchers. So that is the main reason why we are going for open resource. It doesn't mean like these are nothing less than any commercial available softwares. Okay, so even in fact, the foolproof suite is the first or first software which has been developed and tested. Even it started in 1996. So before 1996, they have started this developing a foolproof, and this foolproof is developed by Rodrigo, who is a principal scientist at Institut Laval Langevin in Grenoble, France. So ILL, which is normally known as ILL. So they have this is your neutron diffraction and also neutron facility. You have all kinds of neutron diffraction, neutron CT, neutron scattering, and all the things. Even bio application you have in ILL. So he is the main. He is one of the main scientists who is beyond this foolproof. So we need to first. So I thank him because for making it free for all the researchers. And then recently we have something called as Vesta. So Vesta is again it is developed to support foolproof. So this Vesta is almost similar to your diamond or crystal maker or any commercial crystal drawing softwares. Then we are going to also use Quellex and also POWCOP. So these are for phase identification and phase matching. So these we are going to use it. And Powdle is the software which is normally used for converting the data. Okay, so you can get data from different machines, but then if you want to keep a common format, you can use Powdle. So we are going to use all these things, and also materials project.org. This is again a uh, open source crystal information website where you can also download the zip files and all those things. Okay, so these are things which we are going to extensively use in our workshop. And then even when I prepared my talk, most of the talks it's not just my contribution. There are also from some other resource persons like Stan from ICMCB, where I did my PhD. So he has also shared a lot of information for this PowerPoints and all the things. And also one very good for learning your ritual refinement is Scott Speakman from MIT. So if you use this website, so you can get a lot of information on X-ray analysis, not just ritual refinement. It is also he has given a very good PowerPoints for all kinds of uh, uh, X-ray analysis. It can be a microstructural analysis, it can be a crystallite size analysis, or it can be a stress or like strain analysis. All this, okay. So this is why I have put first slide. So we need to. I thank all these people who have really inspired and who are given their lot of time and their energy to have this kind of open source. So before to this next main topic, so I have already sent a link for everyone. So you need to install your full pro Vesta, Quell, and also PO DLL. So this will be useful when we go for next sessions, like session 3, session 4, and all those things. So first session is just only the introduction, so it's not a problem. But when it comes to the next sessions, it is better you try to download this. So and also I have given the main link, so the main website links, so you don't have to worry about your any spam or any kind of malwares. Okay, so you can directly download those things from the main website. Okay, so now coming into this, coming back into our uh, this particular workshop. So we have got application from several people. So as Suresh sir has already explained, we got around 150 participants. So out of this 150, 20 people are from abroad. So you have uh, this is a very general share I did here. And also when it comes to background, so we have all people like we have faculties around 30% of faculty, and most of them are research scholars. So this is very good because uh, they will be using this uh, software and all these things in their thesis. So uh, so this is very good. So I look forward for very active from everyone. Even we have some UG and PG students. So that is also I welcome everyone, all of you to this seminar. Okay. So with so let us go to the so this is the roadmap. So don't worry, we'll skip this. So to start with, so we need this X-ray. So main reason is so if we are able to see something, is mainly because there is some phenomena such as reflection or diffraction. So if there is no reflection, then we cannot see. It's very simple like that. Simple concept. The same thing. This is the same concept which has been used in your microscope. So you keep your object, then you some visible light, and then you have some things which would help you to magnify those. And what is this magnification? Magnification is nothing but it is mainly uh, depending on the size of the object and also the wavelength of your light. You can see different uh, scale of. Okay. So this mainly depends on your. So this is again based on your very basic physics uh, principle that any scattering or any diffraction will occur only when your object size is almost equivalent to the size of the light. Okay, so even when it comes to night, we don't see in the night because there is no. This is very simple way of defining this. And when it comes to X-rays, why we need X-ray instead of just a microscope? So X-rays are mainly used. They call it we can call them as a super microscope, your X-ray diffraction or your X-ray scattering. So the reason is when it comes to objects, if you use wavelength like normal laser light, you can see objects which are in micron size, not below that. So when it comes to your but when it comes to your material, materials normally made of a lot of atoms, and atoms, the arrangement of atoms would actually give the physical property and also the strength and all those things for a material. So if I want to see atom, then I need to use a light which is having almost similar wavelength, and X-ray is one of those light which is having that kind of wavelength. So the wavelength of these X-rays are in angstroms. So even if you take size of the atom, it will be almost in angstrom. So that is why these X-rays are on X-ray diffraction, X-ray scattering is normally termed as a super microscope. But only difference compared to your regular microscope and X-ray diffraction or scattering is, in case of microscope you can see the light, visible light, but in case of your X-rays you cannot see the or feel the X-rays. They can penetrate, they can just pass your body, but you cannot feel them. So to have a feel, what we do, we normally use some devices such as photographic film. We giving information how the X-ray is interacting with the crystal, or you can also use some modern computers with some softwares which you do some Fourier transformation of the data which you get from this detector. Okay, so this is the only difference between your X-rays and microscope. Microscope you can directly get the information, but for X-rays you need a secondary device, maybe like a photographic film or computer. Okay, so now when it comes to X-rays, so why X-rays? As I told, so the X-rays are having wavelength of 10 raised to minus 10 compared to your visible light or ultraviolet ray, which is having higher uh, wavelength. So now, if you take the atoms also, the atom size is almost equivalent to almost in angstroms, 10 raised to minus 10 meters. Okay, so these X-rays are those are the lights with very small wavelength, and they are far away from visible region, and hence uh, we cannot see them. Instead, we have to use some kind of detectors to get the feel of these X-rays. So that is what I explained in the previous session. So now if you take X-rays, they can distinguish the atoms. The reason is, if you take the size of atom, this is your size of each atom. So each atom is having a different size. So you even starting from potassium 2.03. So if you go from potassium to your krypton or selenium, so you can see there is a variation of size. So this is actually you can see the so your X-rays can actually distinguish the atoms. Okay, so that is the main advantage, or this is the main basic principle why we use X-rays for studying the materials. Okay, so so this is again just a, very simple diagram to show the scale of the size, or the size with respect to the objects. Okay, so you have you can have objects which are in subatomic which are subatomic, which will be around zero point 0.1 nanometers. So for this, you need to use some method, something called as particle accelerator, if you want to see that. If it is anything around, or even you can use uh, TEM in this case. So, but when it comes to atoms, so which are in 10 angstroms or 1 angstrom, so you can again you need to go for or something. And if you are having a particle, then you can use a scanning electron microscope, which would give a resolution maybe up to 50 nanometers, or FASM. If it is FASM, then you can go up to 5 nanometers. Okay, so these are different techniques that you can use. So X-ray would fall somewhere in between this range. So between uh, maybe 10 nanometers to 100, maybe 100. Okay, so these are something which we have, and then beyond that we have optical microscope which can detect in micron size particles. And when it comes to our normal just eye, then we can go from 100 micron to maybe 10 meters or even beyond. It depends on your visible power. Okay, So now, when it comes to X-rays, you can have one. It is not just only diffraction. You can have a lot of other things. So when you send your X-ray on an object in the sense any material, so you can have a transmission. This is something like you send your light to a glass. So if you have a glass piece, and if you shine the light glass piece, what is the possibility? The light can pass through the glass, which is your transmission, or you can also have something called as a reflection or diffraction. So reflection or diffraction is nothing but so reflection is nothing but light which is coming back to the medium, or maybe it is changing its direction. So this is the second phenomena. So apart from that, you can also have a lot of other things. So so you can also have some scattering and all those things. So let us come back only, or let us stick ourselves only to our transmission, diffraction, reflection. Okay. So when it comes to transmission, diffraction, and reflection, so this diffraction is normally used to study uh, the structure. So the reason is, crystal structure is not, it is the arrangement of your atoms in a given material. So normally your Bragg's law is the one which we use in detail, or which is the basic principle behind this X-ray diffraction. So your peak position, when it comes to peak position, it will appear only when you satisfy a Bragg's condition. What is this Bragg condition? N lambda, I is nothing but lambda. Lambda is your wavelength of your rays, is equal to 2d sin theta. So this d is what we call as the interplanar distance, or distance between two planes. So this again I will explain in the next slides. So if only you can have a diffraction peak. Okay, so that means only when you have a constructive interference, then you can have this kind of peak. Okay, so this is how it. This is a schematic, or this is how we have a animation. So you take two parallel lines of X-ray. So this is similar to something what you have in your Young's double slit experiment. So when you have constructive interference, you can get a bright band. When you have a destructive interference, you get a dark band. So the same principle applies for this kind of X-ray diffraction. But only thing is here the light is a X-ray light, not just a regular light, visible light. And also the scattering, the slit is nothing but it is each atom. Each atom is going to diffract or reflect the light. Okay, so your X-rays. So now if you take these two rays which are coming and falling, you can have the first ray is falling on the first atom which is in the upper uh, or the first layer, and the second ray of X-ray is falling on atom which is in the next layer. So these are parallel layers of atoms. So as planes. Okay, so crystallography planes. Crystallography plane is nothing but it is just two planes of or two parallel planes of atoms. Okay, so if you take this kind of diffraction, then what happens? Depending on the reflected light, if they are constructively interfering, then you get a peak in the X-ray diffraction. If it is, you don't get any peak, so it is just destructive interference. So then when it comes to planes, so normally you need to have some very basic knowledge on the your Miller indices and all those things. So what I will do is I'll just shift to one more slide where I will give a very brief introduction for your crystal structure. So you need to know, you need to have a very basic idea of crystal structure. So what is the meaning of crystal structure? It is a structure of a. It is nothing but it is just a combination of your lattice and motif. Lattice in the in the sense you have the lattice is nothing but it is the points which are in the plane, which are the points which are at equal distance. And then motif is nothing but it can be a single atom or it can be a group of atoms. So that is your crystal structure. So normally, if it atom, it is made of lot of so any material. For instance, it is made of lot of atoms. So these atoms they are arranged in certain or repeated way pattern to form what we call as the crystal structure. Okay, so this crystal structure again. So when it comes to crystal structure, then you have very simple structure which can be repeated with what we call as a unit cell. So if I take this unit cell and then if I repeat it in all three directions, then I get a I get a complete crystal. So this is your crystal. So if I take this crystal, then what happens? This is made of one single unit cell, which is repeated in x direction, y direction, and z direction. Okay. So this is a very basic structure that can be repeated to get a crystal. So that we call it as a unit cell. So what the importance of this unit cell? The unit cell would give the shape of a given crystal or the symmetry of a given crystal. So, for example, if you take a simple, this is a body center cubic. A would be equal to B equal to C, and also alpha, beta, gamma would be equal to 90 degree. So this would be your body center. Then there is something called as simple cubic. Simple cubic or primitive cubic is nothing but you have atoms only in the corner of the cube, and A is equal to B is equal to C, alpha is equal to beta is equal to gamma. So I may not go in detail because it would be difficult to cover all the things. Only I will just give a uh, very summary of these crystal structures. So as most of you would know, if you're from physics or chemistry, it doesn't matter. So you would know like there are 7 crystal systems, like your cubic where all sides are equal and all the angles are 90 degree. Tetragonal, 2 would be equal. The third side would be slightly different, and all sides are all angles are in 90 degree. And orthorhombic is the next one where you have all sides are different. So the size of all sides are different and it's still 90 degree. And when it comes to rhomboidal, it's all sides are equal, but one of the angle is not equal to 90 degrees. So there is some tilting of your unit cell. So the same thing with hexagonal and monoclinic and triclinic. So as you go from cubic to triclinic, the symmetry would be will be decreasing. What is the meaning of symmetry? Symmetry in the sense, if I take the even if I turn it by 90 degree, what happens? It would still looks the same because it is difficult to distinguish the cube in any different direction. Okay, so but when it goes to monoclinic or hexagonal or triclinic, then what happens? If I stand in front of B, A is longer. If I stand in front of A, then what happens? B will be shorter, A will be longer. So so it won't look the same. So this is what we call as the symmetry. Symmetry will be lost when we go from, or this is going to decrease from cubic to triclinic. Okay. So these are the 7 crystal systems that you would have already studied. Then this is about simple cubic. You need to know the number of atoms. So if I take simple cube, then there is total number of atom in a unit cell is 1 because there are 8 corners and one it is shared with neighboring cells. And finally, what you have is 1 atom per unit cell. And when it comes to center, then you have 2 atoms. So these are the things which you would have already learned in basic things. And even for face center cube, so in this case, what happens? You have atoms in all the face. Okay, so on all the face you have one atom, and this there are 6 face, and half each is having half atom. So total would be something like 4 atoms. And when it comes to body center, there is an atom which is in the center of the cube. Okay, So now you need this kind of what is the importance of your interplayer spacing. So interplayer spacing, if you take DHL, it is the distance between two parallel planes. So in this case, if I take 001, so which, how do you define this? This is again based on the your crystallography. So again, if you take this is Miller indices. Miller indices is nothing but it is the reciprocal of your lattice parameter. Okay, HKL would be equal to like 1 by U, 1 by V, 1 by W. And what is or A by B? Sorry. What is this UEW? UEW are the uh, intercepts, and HKL are the your Miller indices. Okay. For example, if I take this simple body center cubic, then what happens? If I take this is the origin, because you can choose any one of them as a origin, because if I take a crystal, this crystal, I can either choose this is my unit cell, or I can choose this is my unit cell. It doesn't make any difference because all the unit cell are same. So what I will do, I'll just take a unit cell and I'll choose one of the atom as the origin. Okay, so this is your 000. Then what happens? There is one atom at let us, if I call this as a unit cell, what is the meaning of unit cell? Then A is equal to B is equal to C is equal to 1. Okay, 1 centimeter, 1 angstrom, or whatever it was the unit. Okay, so this is unit cell. If it is a unit cell, then what happens? Your A is equal to B is equal to C. So in that case, what happens? Uh, this atom would be at distance of 1 units in the x-axis, and if I take this atom, it would be at distance of 1 unit in the y direction, and this atom, the top one, would be at distance of 1 unit from the in the z direction. Okay, so this is your units. And then if I want to say what is the co and if I take the coordinate atom with respect to this atom as origin, then what happens? It will be 100 because you don't have any displacement in y and z direction. Okay. Now, if I want to tell uh, what is the coordinate for this particular atom, then what happens? Say what is the coordinates for this atom, then what happens is you need to, if I want to reach this point, then what happens? I have to travel 1 unit cell on the y direction, again 1 unit cell in the x direction, okay, x and y direction. So from here to here it is 1, and then from here to here it is 1. So if I want to say the coordinates, then it will be 1 1, and then I don't have to travel in z direction, then it is a 1 1 0 is the coordinate for this particular point. So now how to convert this into a your this is your UEW, which is your uh, code your intercepts. So how to convert this into HKL? This is, uh, A by B, sorry, A by U, B by V, and C by W. Okay, so A, B, C are your unit cells. So in this case, all the sites are in 1 equal to 1. Hello. Okay. So there was some problem in the internet. So sorry for that. Okay. So we were. I was talking about the Miller indices. So Miller indices is nothing but it is if I take HKL, HKL is nothing but it is the reverse of your intercept. Okay, 1 by U, 1 by V, and 1 by W. Okay, so these are your Miller indices. How to define a Miller indices? So in this case, now if I want to take for this, for example, for this atom, so first I need to know the intercepts. Intercepts are something like you have one, and infinity. Infinity because you are not touching your z-axis in this case. Okay. So now if I want to take HKL, then what happens? It will be 1 by 1, which is 1, and then 1, and 1 by infinity would be something like 0. Okay. So these are the what we call as the okay. So this is what we call as a Miller indices for a given atom. Okay. So this unit cell is a very basic thing. Then this is the reason why I'm talking about this is you need to know something called as the interplanes and interplanar distance. Okay. So now, so if I go to the next thing. So this plane is 001 plane. The reason why it is 001 plane is again you are going to use the Miller indices. So again and then you are going to calculate this. Okay. So what is the use of knowing this interplanar distance? So for example, if I know that this is normally given as HKL. DHKL is normally what we call as the interplanar distance in the Bragg's equation. Okay. So now if I know the distance between these two planes, that means I know the if this is your so this is your x-axis, this is your y-axis, and this is my z-axis. So then if I call this is my a parameter, and if I call this as my b parameter, then if I call this as a c parameter, then if I know this DHKL distance, then what happens? I know the value of c. Okay, or I know the value of one of the lattice parameter. So this is how you get the unit cell parameters ABC. So if I know D001, then I know the C. If I in the same way, if I know D100, then I would know the value of A. And if I know 010, then D010, then I can know the value of B. So this is how you can actually find the unit cell parameter. So for this, what we do is we do a diffraction. So for example, as we discussed, so if I have a first ray which is coming from here and hitting the first top layer, and then the second ray is coming here, and if it is hitting the second atom in the same plane or same axis, then what happens? If this is having a constituent difference, then what I get is the distance between D001. Okay, so the distance between these two things. So that is how we can actually find the parameter. Same thing, if I rotate this by 90 degrees, then what happens? Your first ray would hit on this, and then the second ray would hit on this. Then what you get is the distance between these two planes, which is your D uh, 010. D010 is nothing but it is your B lattice parameter. Okay, and if I further rotate this unit cell, then what happens? I would have maybe the first ray hitting this uh, atom, the second ray is hitting this atom, then I get the distance between these two planes, which is your D100, which is nothing but I get the A parameter. Okay, so this is how you can relate your DHKL with your ABC parameter. Okay, so again for that you also need the help of your angle of your reflect or Bragg angle, what we call as theta HKL is nothing but your Bragg angle. Okay, so this will again come back later. So now when it comes to, so these are some about your planes and all those things. So I'm going to share this PPT. I cannot cover everything. So what we'll do is I'm going to share this. Then you can have the you can go through this. Okay. So but I'll just try to explain this. So how to get a what is the relation between your DHKL and your A parameters. Okay, and HKL values. So for cubic system, if you take cubic system, A is equal to B is equal to C. So in that case, what happens? So in that case, what happens is your AB the numerator would be is just A square. So your equation would be something like this. Okay, 1 by d square is equal to h square plus k square plus L square. So if I use this, then what happens? D square is nothing but, or A square. If I take A square is nothing but h square plus k square plus L square by A square. Sorry, D square. Okay. So this has to be A square. This is your A square. So from this, A would be square root of HKL by D. So this is how you get your lattice parameter in case of your cubic. The same thing is for tetragonal. Tetragonal A is equal to B, but it is not equal to C. So it would be something like this. And then orthorhombic would be using we would be using this relation. Okay. So when we go when we find the ABC parameters, we may not actually do all these calculation. Instead, the program would be doing in the background. So that is the reason I'm just trying to explain this. But you should know how you get this. So that is because this is very basic things. So I am trying to just go through these things. Okay. So similarly, you have different relations for different systems, crystal systems. Okay. So indexing again, we'll come to this at a later stage. So what I would do is I would stop at this moment and then I will go back to our previous slide. Okay. So now you know the importance of your crystal planes. So crystal planes, for example, if I take simple cubic, so what are the different possible crystal planes? So the different possible crystals planes are your 100, 110, 111. Okay. So these are, or it can be 010, 001. So you have to have a combination of this, or in this case it would be 101 or 011. So there will be different planes. So based on where the X-ray is falling. Okay. For example, if the X-ray is falling from the top surface, then what happens if I take this is your y-axis, x-axis, and z-axis. So if you're allowing the X-ray to fall on this plane, so then what happens? You are having information about the P001. Okay, so in this case, but if I want to have 100, then it should be something like this is X and all. Okay, so next in the same way, if I take BCC compared to your simple cubic, there is one more atom which is in the center of your in the center of the cube or your unit cell. So now what happens? There is an extra, or there is one more plane which is in between your 100 and other things, so which we call it as 200. How we get this as 200? It is very simple. So we use the same concept. We need to know uh, what is the coordinate of this. So in this case, what happens? You need, if I want to reach this point, I need to travel uh, zero point 0.5 in the x. So if this is your x direction, then what happens? It is a 0.5, which is nothing but half of the unit cell. So I have to travel 0.5 on x-axis. Then you don't have to travel anything on y or z. So this is 0, 0. So now if I take this reciprocal, then what happens? Sorry, this is infinity and infinity. So if I take reciprocal of this, then what happens? 1 by half is nothing but 2, and then 1 by infinity is 0, 1 by infinity is 0. So this is how you get to this HKL of your body centered atom. Okay. So then you have different planes. So when your crystal is rotating, you get diffraction from all these different planes. Okay, so that again we will see later. So now if I take this for example, so this is similar to what we discussed. So if I take this particular unit cell, there are more atoms in even in the middle. Then you can also have a possibility of having D110 and also D220. This is similar to what I explained in case of your body center. Okay, so how you get 200? The same way you can also have 220, which is half of your 110. Okay, so it depends again on the atoms, the number of atoms which are present in a given unit cell. Okay, so this is again NaCl. So this is how I was trying to explain. When you have rotation of your unit cell, you will expose different crystal planes. So when you have different crystal planes, then what you get? You get different DHKL. Okay, for example, in this case, you can get D220. So in the previous case, it was very simple. It is either D001 or D100 or D010. But you can also have different planes based on the orientation of the crystal. So this is about your crystal planes and the interplanar distance. Okay, so now if I get a peak in case of your HKL. Okay, so sorry, in case of your NaCl, so this is your example of NaCl. So we would say this peak is corresponding to 200. What is the meaning of that? Is nothing but if you take NaCl, this is the unit cell of your NaCl, and now if you see you are having reflection or your diffraction from these atoms. So this is the first atom, second atom, and this is the third atom. So when you have this kind of diffraction, so instead of uh, 100, you would have your diffraction from T200. Okay, so this is your diffraction of 200 plane. So now if I know this, what are the things I know is I know it is from 200. So I know the DHKL. Then I also know the peak position, which is nothing but theta HKL. Theta HKL is your Bragg's angle. So Bragg angle appears only when you have constituent difference. Okay, so what you need to remember here, when you want to satisfy this Bragg's law, the angle of incidence has to be equal to angle of diffraction. If it is not equal to angle of diffraction, then you will never satisfy this law. So in that case, you will have only destructive difference, not the constituent difference. So for constituent difference, your angle of incidence should be always equal to angle of reflection. So only then you can have you can satisfy the Bragg's law. If not, you cannot satisfy the Bragg's law. Okay. So when it comes to diffraction, how the diffraction occurs, so you need to. This is a very simple, this is the oldest diffractometer. So what they used to have is they used to take a lead box. So this is like your circular uh, some tiffin box or some box. So normally this would have a lid which can go on top of this. So normally, so what they used to do is they used to put the sample, either a single crystal or a or a powder, in the middle of this box. Okay, they used to keep the sample here. Then they used to send the X-rays from this X-ray generator, and then the X-ray used to fall on this crystal, and based on the which plane is diffracting, you would have diffraction in different planes like this. Okay, so for example, this may be in one plane, and then maybe you would have a second plane which is be in a different angle. Okay, so this angle, this would be your angle of incidence or the Bragg angle. So you would have a diffraction from the crystal, which is shown here. Okay, so normally what they used to do is they used to put a crystallographic or photographic film. So they used to just put a film here. So this is similar to what you had in the cameras, previous cameras. So you had cameras with rolls. So that role is what we call as the photofilm. So whenever you have light falling on that roll, then that reel, then what happens? You used to get some lines, okay, or it used to make some markings. If not, it used to just be a black, okay, or dark film. So they used to put this kind of photo film on this in this circle. Then what is they used to do is to close this box with one more lid and start the X-rays. So when you have this kind of diffraction, then what happens if you take out the film after exposing, then you would see some lines like this, okay? And then based on these lines, so this would be you need to find the distance between the center and the given line. So this is the center spot. Then what happens? This would be the line which is coming from this point, and the other line would be coming from the other point of interaction, okay? So you would get this uh, distance, and then they used to find the lattice parameter and the symmetry and all this, okay? So this is very old technique which you used to be maybe 30 20-30 years before, but we don't have to go through these drills anymore. The reason is, so the disadvantage would be like each experiment would need a new photographic film. So that means if I have one sample, I used to use one photographic film, and if I want to do the diffraction on second sample, then I have to bring a new photo film. Okay, so this is each sample used to, or each experiment used to have a new photo film, and then analysis would take a lot of time. Okay, and you should be very good crystallographer if you want to explain this kind of things. Okay, so now, before going into modern X-ray diffractometer, I will just talk about some other techniques apart from diffraction. Okay. So in the previous case, in this case we studied only about the diffraction. Okay, transmission or diffraction. So now, what are the other things what that can occur when a X-ray falls in a material? Okay. So apart from your transmission or reflection and diffraction, there is something called as scattering. Okay, so the X-ray, when it falls on an object, you can also have X-ray scattering. So this scattering can be again two types: coherent scattering and incoherent scattering. So normally your incoherent scattering is used to image your molecules or atoms, and when it comes to scattering, this can be used for more atomic or molecular level uh, structural information, such as in case of your SAX, small angle X-ray scattering, or to get a pair distribution function. Okay, so these are the things that you can get from scattering, or these are the information that you can get from scattering. So there is something also called as absorption, fluorescence, and also near edge and electron emission. Okay, so these kind of phenomena would give material characteristics such as your elemental analysis and the local structure of your material or your atom. Okay, and it also give coordination. For example, in case of your X-ray photoelectron spectroscopy or XPS, if I take XPS, what happens? You send high energy X-rays, and then this X-ray would knock off the outermost electron, and this electron would be detected by a detector, and based on the electron, you could give the coordination in the sense, if I take for example cobalt can be in 2 plus or 3 plus or 4 plus. How to know this? You just have to do your XPS. Okay, so if you do this XPS, then what happens? You get the information about the coordination is what is the oxidation state of your element. Okay, so these are the different things, and also you can have something called as fluorescence. Again, fluorescence is in XFS, which is your X-ray fluorescence spectroscopy. So to know what kind of element is present, so similar to your XPS, but only thing, you cannot know the coordination in this case. So you can know what element is present, but you cannot know the what is the coordination. Okay, so you know it is a cobalt, but you don't know whether it is in 2 plus, 3 plus, or 4 plus in case of XFS, fluorescence spectrophotometer. But in case of electron emission, which is your XPS, then you can know the coordination. That is the difference between XPS and XFS. Okay, and then you can also have the transmission beam. So by using your transmission beam, you can also do high resolution imaging. Okay, so in this case, so then what is the difference between different X-rays? So you see X-rays in your labs, and you see X-rays in some medical scanning, and also you see some X-rays in airport. What is the main difference between all these X-rays? Is it is the it is nothing but it is the energy of these X-rays. So where in case of your lab X-ray, your the energy would be something around 2 to 5 kilo electron volt. It would be less than 10 kilo electron volt. But in case of your medical scan, it would be around 10 to 20 kilo electron volt. So this will be what we call as hard X-rays. Um in case of airport, it would be much higher. It would be in 100 kilo electron volt. But normally these are used only for material testing, not for humans. So if you send these kind of hard X-rays on humans, then you can have cancer. You can create some cancer cells. Okay, so that is the reason why we don't use hard X-rays in case of your crystallography. Okay, normally this is done in uh, airport or something like that. Okay, so now there are different diffraction techniques, not just X-ray diffraction, but also there is something called as electron diffraction and also neutron diffraction. So what is the difference? Main difference: X-ray diffraction, when it comes to X-rays, X-ray normally interact with atoms. Atoms in the sense not exactly atom, but the electrons. So it is a electromagnetic interaction. X-ray diffraction is mostly electromagnetic interaction.
You see, what is X-ray regarding
So,
X-ray?
sorry. So, can you please repeat? Hello. Okay. So we'll come and I will again discuss what is X-ray. So how to generate X-ray. So I will cover that in the next slides. So I'm just giving this is very general difference. It's not like I'm not going in detail. So when it comes to X-rays, this X-rays, they interact with atoms, and to be more precise, it is not atom; it is the electron, the outermost electron. So it is the electromagnetic interaction. So then, when it comes to electron diffraction, this is very similar, very much similar to your X-rays. But when you're going to neutron diffraction, the neutron. So instead of X-ray, you're sending a neutron, which is your gamma ray. So this neutron can actually interact with the nucleus. Okay. So in this case, it's the elastic neutron scattering. So when your neutron is interacting with the nucleus, you can also get what we some magnetic spin uh, structure or magnetic structure of the material. Okay, so this is something like it is a high end or it is a improved version of your X-ray diffraction. Okay, so but when it comes to the next column, you can see X-ray is widely used because it is more convenient and also it is economical compared to other things. Okay, so this is mostly more widely used technique in case of metal characterization. So you can find in most of your labs this X-ray diffractometer. Then when it comes to electron diffraction, this is the next easily available. I don't say it is very common because the reason is you may not see uh, TM in most of the labs. You can have maybe one TM for a institute. Okay, so something like that. But when it comes to neutron, this is very special and also it is more expensive and very rarely available. Okay, so this again we'll see in the next slides. Okay, then this is again just what I explained. So when you take X-rays, X-rays would interact with the valence electron, which is your electromagnetic interaction. So in case of electrons are charged particles, so they can interact with the matter and also the atomic nuclei. And when it comes to your neutron is they carry some spin, magnetic spin, so they can interact with the nucleus, and also they can be tuned with by applying a external magnetic field. So these are the difference. And when it comes to penetration depth, these are the penetration for each of them. So X-rays would have 10 raised to minus 4 electron volt penetration. Sorry, length. So it is this is the energy. So normally you have a nominal penetration, and when it comes to your electron, they can have better penetration, but not as good as your neutrons. Okay, neutron would have a higher penetration compared to any other techniques. Okay, so when it comes to X-ray, again there is something what we call as a synchrotron X-rays. Synchrotron is again a high energy X-ray diffraction. So there are the reason why we cannot see this in all the places. It is very rarely available. Okay, so these are this in this slide I'm just showing all the most of the facilities that you have around the globe, not just India but around the globe. In India, we have only one center, which is your RRCAT, which is Raja Ramanna Center for Advanced Scientific Advanced Characterization Techniques. So this is RRCAT. We have something called as Indus 1 comma 2. So this is in Indore. So this is the only neutron facility which is in India. But when you have more in Europe and you even in US, okay, and there's a bunch of neutron facility, sorry, synchrotron facility in Japan and Korea. Okay, so apart from that, you don't see this in common. Okay, so this is not a very common technique. Instead, it is a very uh, rare technique. Okay, and then when it comes to neutron facility, as I told, it is very high or it is very expensive technique. So here you can see in North America, there is around in the entire America, you have around 5 to 6 facilities here. Okay, so you won't have more than that facilities. Okay, most of the facilities are in Europe. So in France, there is two. You have in Switzerland, UK, and other places in Germany and all those things. Okay, so this is very rarely used or very less available uh, centers. Okay, when it comes to India, we have one center in which is in Bombay, your BARC. So BARC, they have this neutron facility, and this is called as Dhruva. So this is the one which is shown here, Baba Atomic Center, Bombay. So they have this neutron facility, only one in entire nation. So even when it comes to Asia, there are uh, very few neutron facilities. Okay. Okay, so now when it comes to X-ray diffraction, why X-ray diffraction is so much important? So we have more than 50% of participants are research scholars. So if you take if you are doing any experimental research, you may be doing in physics or chemistry. First thing what you do when you prepare your sample, you may prepare sample like some solid state ceramics, something like your perovskites or some spinels or some layered materials. Okay, or you may be even doing your nanomaterials, synthesis of nanomaterials like titanium oxide, TaO2, CDSC, CDS, or some other gold or silver nanoparticles. Or you may also be depositing some thin films like your barium titanate, like your which is your uh, multi kind of multiferrites, or maybe a thermoelectric material or a superconductor, or you may be working on some intermetallics, different kinds of intermetallics, and even in case of industry and something like iron and steel, pharmaceuticals, and cement. The first thing what you do is once you synthesize, the first step, even before you test your performance, maybe like if you're doing your magnetic studies, you may not directly go for magnetic studies. Instead, first thing what you do is you go and do the X-ray diffraction. The reason why you do this is to get the phase purity. Most of the thing is it is phase purity, because you want to know whether you have formed AbO3 perovskites, or is it just some mix of A oxide and B oxide. Okay, that is your phase purity. Then if it is a multi-phase, then you may go for quantification. Then if you are working on a nanomaterial, you may be interested in knowing whether it is crystalline or amorphous. And then when it comes to crystalline, you may again come back and find the crystallite size, and maybe in some case stress and all these things. Okay, strain and defects. But if you take any of these materials, the first thing what you do is diffraction. Okay, so in this workshop we'll try to cover most of these things other than the reflectance, last one. Okay, we may not have this sufficient time to cover this thickness or reflectance, but we will try to cover most of these things: how to do a purity or phase identification, and how to find the stress or strain or crystallite size. Okay, so in our workshop, this is what we are going to learn. Okay, even if you don't know anything about phase purity, phase analysis, you'll learn step by step. So that is the main aim of this workshop. So then why it is important? For example, you may be doing this is very classical example, because a lot of people would be working on this kind of titanium oxide or zinc oxide, or maybe some other simple oxides. So even if you take some titanium oxide, which if you just do a Scopus or uh, search, you would get maybe 10,000 more than maybe 15,000 papers. Okay, still what are the importance is, if you take titanium oxide, it can have either anodized or rutile, apart from bromchloride and all those things. So I'm just sticking only to these two different phases. So if you take a band gap, so both are having almost close band gap, 3.2 and 3.0, which you can even have due to size effect. Okay, and when you take the refractive index, even refractive index would be something very close. Okay, but only thing is anodized is optically negative material, while your rutile is optically positive material. So how to distinguish, even if you take your appearance would be almost similar. Okay, so your anodized and rutile would be they will look almost similar. Maybe one of them is slightly yellowish, other one is slightly white. But if it is if you are doping something, maybe something like if you are doping some iron or manganese or cobalt or something on your titanium side, or even instead of oxide, if you are doping some sulfur, fluorine, all those things, then it is difficult to know whether it is a anodized phase or rutile phase. So the best thing or the only way to know this phase is by using your X-ray diffraction. Okay, so you can see this is your X-ray diffraction for pure anodized phase, and the top one is for pure rutile phase. Based on your experimental condition, you may have some mixed phase. So this is the one which is something like a mixed phase. Okay, so this is what you are going to learn in this workshop: how to identify whether it is pure anodized, pure rutile, or whether it is a mixed phase. And even if it is a mixed phase, you can also find the weight percentage. So what is the weight percentage of rutile, what is the weight percentage of anodized, by doing a X-ray your ritual refinement. So this is what you are going to again learn in this workshop. Okay, so there is one more example. This is from my work. So we have done some work on this. So this is your SRFE O3, and based on the oxygen stoichiometry, you can have different kinds of your materials. Okay, so in this case, for example, if you take this anodized and rutile, so anodized is low temperature phase, or it is at low thermal equilibrium. If you go higher temperature, then what happens, this anodized is going to get converted to rutile. For example, if you take your anatase powder and if you start heating at 600, 700, 800, so after 800 it will become rutile, and this is irreversible. You cannot bring back again this rutile into anatase. So this is a irreversible process. But this in this case, what happens if you keep changing this oxygen, so oxygen concentration or the stoichiometry, you can have reversible reaction. Like if you take this O3, so this is a cubic symmetry, and if you remove some oxygen by just heating at high temperature, then what happens? This will become a tetragonal symmetry. Then if I further reduce oxygen, then what happens? This will go to orthorhombic. Again, it will go to lower symmetry like orthorhombic. Again, this is orthorhombic, but with lower symmetry. Okay. So this is something which you can identify only through your X-ray diffraction. Okay. So and then if I start putting oxygen into this structure by either high pressure oxygen annealing, or by electrochemical insertion of oxygen, then what happens? I can go from 2.5, which is your orthorhombic, to a more symmetric or highly symmetric phase, which is your cubic. Okay, O3 is cubic. Okay, so this is these things you can study, and again based on the oxygen concentration, your physical properties would change. Okay, so this would be more ferromagnetic, and this is a very weak magnetic. So this is antiferromagnetic structure. So these are the things which you can actually alter, and this is when it is a cubic, and if it is highly symmetric, along with ferromagnetism, you can also have good conductivity. So this can become a metal. So when you go for uh, oxygen deficient sample, this is like a semiconductor or insulator. So this is how you can tune the physical properties of a given material by doing different things. Okay, and X-ray diffraction would help you to uh, uh, study in depth. Okay, so when it comes to X-ray diffraction, so in the previous case, I took a very old technique which is using a photo film. Okay, now in this case, what we do is I will show you the I will show you the uh, modern diffractometer. So this is normally your modern diffractometer. It can be Philips X-ray diffractometer or Rigaku or your Bruker, anything. So most of these diffractometers will have some all these features. Okay. So the first thing is your X-ray tube. So this X-ray tube would generate your X-rays. So again, we will see how to generate these X-rays. Then you will have something called as solar slits and divergence slits, mask, and all those things. I will explain one by one. And there is one thing what we call as a sample stage. This is the sample stage. So where you actually keep your sample, and then so the diffracted X-ray would should be detected by a detector. So in this case, we can have either gas detector. So this is your gas detector, or if you take any very recent diffractometers, they would have a solid state solid state detector is ultimately it is a photo detector which can actually detect the X-rays. So this photodiode would be programmed, or it would be set to detect the X-rays. So this is the structure. So we will see one by one what are these things, why you need a monochromator, why you need a solar slates. So all these things I will explain one by one. Okay. Yeah. Okay, so this is just a skeletal representation of all the things what we see in the this one. Okay, so if I just remove the goniometer and all these things, so you may ask why you need this goniometer. Goniometer is nothing but these are two wheels. The first wheel is connected with X-ray tube and the left part. So this is sitting on this first wheel. There is one more wheel in the behind. All this right hand side, which is your detector, monochromator, all these things, these are sitting on this second wheel. These are your first, when your first wheel is moving, that means all this left part is moving, and when your second wheel is moving, then what happens, all these right parts are moving. Okay, so this is how you change the angle of incidence and angle of uh, diffraction. Okay, so okay, so this is the skeletal, means I have just removed all the parts. So when you take x-ray, x-ray is nothing but is a beam of light. So this, when it is when it is traveling, so even if you take a torch and if you just shine the light from the torch, what happens is this light is going to scatter as it is moving in the air. So because there are some dust particles and all those things, each dust particle would scatter the x-rays, sorry, your light. So instead of having a narrow beam, what happens, this light would scatter in the air. Okay, so even though your torch is having a very small opening, when it falls on a very far away wall, then what happens, this beam would be enlarged. This is mainly due to the scattering which would occur during the traveling of your x-rays. Okay, sorry, your light. The x-rays are nothing but these are also light, but high energy or uh, very small wavelength x-rays. So sorry, light. So then what happens, these will also scatter when they are traveling. Okay, so your x-ray tube is generating this x-ray light, and when this is coming out, your x-ray is coming out, which is nothing but your light is coming out, and when it is traveling, it is going to diverge to focus this. What we have is, we have something called as solar slit and your divergence slit. Okay, solar slits are good, will focus in parallelly and in parallel direction, and divergence slit would focus the your x-rays in perpendicular direction. Okay, so this is like parallel and perpendicular conditioning of your x-rays. Okay, and this will allow your x-rays to fall mostly on the sample. Instead, if we remove these solar slits or divergence slits, then what happens, your x-ray would fall even on the sample holder. Then what happens, you get diffraction even from the sample holder, and your you will get the rays or the information of your sample holder in the detectors. Okay, so to avoid this, what we do is we use different kind of solar slits and also anti scattering slits. Okay, so this we will see in the how it happens, actually happens in the next slides. Okay, so then what is the meaning of monochromator? Monochromator, again I will explain in next slide with example. Okay, so someone asked, what are these x-rays? Okay, so what are these x-rays? It is nothing but it is the light. Okay, it is a fluorescent light. So how to generate this is, you take a filament, x-ray filament. Sorry, this can be any filament like tungsten filament or anything. So what you do is you apply some voltage to this filament. Then what happens is, this filament will start emitting the electrons. Okay, and then you put a metal piece, you put a pure metal. It can be a copper, it can be your iron, it can be a cobalt. Okay, so we will see that in the next slides. Okay, you put a very you put a pure metal, and then what happens, when this electron is falling on this metal, for example, if it is falling on a copper, then what happens, it's going to emit some fluorescence. The copper is going to emit some fluorescent light based on the applied voltage. Okay, again you have to put the voltage here. So this fluorescent light will have some wavelength. Okay, this wavelength is again changes based on the kind of metal you are putting in. Okay, so you may put a molybdenum, you may put silver. Okay, so you can put different metals based on the metal. So you'll have different wavelength. Okay, so this again I will explain. So this is how you produce your X-rays. X-rays is nothing but again it is a fluorescent light. The only thing we won't be able to see these lights. The reason is it is beyond our eyes cannot detect this, or it is beyond our ability. Okay, so now we'll come to filters and all those things. So if I take just your X-ray, something is wrong. Just a minute. Okay, so if you take this just spectrum, or if you take the okay, so if you take the if you see the wavelength, this is your wavelength on a x-axis and then the intensity. If you take these X-rays which are coming out from this X-ray tube, these will have different kinds of characteristics like K alpha and K beta. Okay, K beta and K alpha are two characteristics X-rays. So now if I send all these rays on my sample, then what happens? Each you get diffraction from each of these uh, uh, wavelength. Okay, you will get diffraction from K beta, and also you get diffraction from K alpha 1 and K alpha 2. So for example, if you take copper, so copper has K alpha 1 at 1.54 and K alpha 2 at 1.544. Okay, so these are the two wavelengths which are separated. And if you see so in the next slides we'll see. So if you take any X-ray diffraction by using both K alpha 1 and alpha 2, instead of one peaks you will get two peaks. Okay, in each place. And if apart from that, if I also send this K alpha K beta, then what happens? I'll have also diffraction from K beta radiation. Okay, so now how to get rid of this K beta radiation is you have to put a filter. So for example, in case of copper, we're going to use some iron piece or iron as a filter. Okay, so this is what you see as a mask here. Okay, so mask is nothing but you just put a thin slice of metal piece like your iron metal piece. What it will do is it will block all those K beta radiation. Okay, and it will allow only your K alpha radiation. And then if I want to again cut off this K alpha 2, then what happens? I need to put something called as a monochromator. So what is the function of this monochromator is it will cut off all the K alpha 2 radiation. It will allow only K alpha radiation. Okay, the only problem in this kind of screening of your radiation is you lose lot of intensity. For example, if you remove K beta is not a problem because this has wavelength which is half of your it has intensity which is half of your K alpha. So in that case, what happens? You may sacrifice some intensity of X-rays which is coming from your tube. But when I put a monochromator which is blocking my K alpha 2, then what happens? The intensity which is in the intensity of the X-ray which is falling on sample would be half of the what it would fall with the K alpha 1 and alpha 2. Okay, so most of the labs until and unless it is a specialized crystallographic lab, they won't use this monochromator. They will have both K alpha and alpha 2 radiation. They would use a mask which would screen off the K beta. Okay, so but most of the labs commonly they will have both K alpha 1 and alpha 2. Okay, so this you have to remember. And then why you need, what is the use of using different metals? So if you see here, uh, if I use different metals, then I can vary the wavelength of the X-ray which is generated. So if for example, if I use silver, then the wavelength of light would be, or the wavelength of X-ray would be 0.56 angstrom. Okay, so this is for only pure K alpha radiation. And if I use molybdenum, then what happens? This would be something like 0.71, and then copper would be giving 1.54, and cobalt would give 1.79, iron would give 1.94, and chromium would give 2.29 angstrom wavelength of X-rays. Okay, so these are the if I want to change this uh, wavelength, then I have to go for this different metal targets. So now, but most commonly, what we do, what is the use is your copper, because copper is cheaper compared to your silver or chromium metal. So copper would be the most common X-ray radiation that is used in most of the your X-ray labs, okay, or in your most of the diffractometers. Okay, so now what is the use of these different types of what is the advantage of using different sources? So, for example, if you take this English penny, or nothing but it is just a coin, your pound coin. Okay, so if you take this coin and if you do a X-ray on this, what happens is you get a diffraction, which would be mainly due to your copper radiation or copper, which is coated on this coin. But if I remove the layer, then what happens? This the inner part of this coin is made of iron. So you can see it will give a lot of noise here. In this case, the reason is uh, you are having iron is the material which is present inside this coin. Only the top layer is copper. So when you are using a copper radiation, so this iron would give a lot of fluorescence. Fluorescence in the sense it is giving a lot of light also along with this diffraction. So in this case, what happens? Even if you take the scan for the same time, same settings, what happens? You can see here for copper it was 350 was highest intensity, but in case of iron, with the same setting, the highest intensity is 400, which is almost 10 times less than the previous one. So this is again mainly because of the copper radiation. So instead of this copper radiation, if I use a cobalt radiation, then what happens? This intensity would increase. So I would get a good intensity, less noise. Okay. Then when it comes to your different source, like for example, this is your cerium oxide nanoparticle. So if I use copper radiation, so I get this kind of spectrum with 1, 2, 3, 4, 5, 6, 7, maybe 8 to 9 peaks. So, but if I do this, if I do the diffraction on the same sample using a molybdenum source, so you can see the molybdenum is having half of the wavelength of your copper. So in that case, what happens? I get more number of peaks. That means I can have, I can do better analysis. Okay, so this is the use of this kind of changing of source. Why you have to change the source? Okay, then when it comes to your divergent and anti-scattering slits, so if what is this divergent slit? It is something like this. They will look like this. So here I am going to decrease the slit size. If I decrease the slit size, that means I get a better conditioning of the X-ray beam. Better conditioning in the sense I get more sharp X-ray beam. So if I use a sharp X-ray beam, then what happens? I get better resolution. Resolution in the sense you get sharp peaks, but at the cost of low intensity. Okay, because as you're sending only very less amount of X-rays, then what happens? You get less amount of X-ray diffracted. Okay, so in that case, what happens? Intensity would be again reduced. But if you use bigger slits, what happens is you get very good intensity, but the thing is you get broad peaks. So this is how you can play with your resolution. Okay, resolution or intensity. If you want high intensity, then you use larger slits. If you want better resolution, that means sharp peaks, then what happens? You need to use smaller slits. Okay, so each one is having its own advantage and disadvantage. Next one is your step size. So these things are controlled when you are doing your X-ray diffraction. Okay, so when you collect the data, you need to take care of all these things, like your different source and also these kind of size of the slits and the mask. Okay, so step size, if you see here, I'm using if I use largest step like 0.1, then what happens? I can finish my experiment very fast. But the problem is you may not resolve or you may get the entire peaks. For example, here I am having a, bigger step size, maybe like 0.1. Then I am going to decrease it to 0.01. Okay, maybe 0.02. So if I decrease the step size is nothing but it is a distance between each points, data points. Okay, so if my first point is at uh, 0 and the second point is at 0.1, then what happens? That is the meaning of the step size. Okay, if I decrease the step size, then what happens? I get better resolution. Again, this is similar to what you have with the smaller uh, smaller slits. But if I take smaller steps, I need to collect the data for longer time. Okay, but you don't have to go too small or too less, too large steps. Nominally, you can use 0.05 is the steps. That means if you are taking first data point at 10 degree, then the next data point should be taken at 10.05, then 10.01, 10.15, like that. Okay, at this is nominal, so this is sufficient for having a good X-ray pattern. Okay, then when it comes to right source, as I told in the previous case, so in case of your even the coin, so you need to choose the proper radiation. Copper radiation is good for most of the samples, but when you are having iron and cobalt, so copper is not good. Like even in case of manganese, iron, cobalt, manganese oxides, if your sample is having this iron, cobalt, and manganese, then better to avoid your copper radiation. Instead of copper radiation, you can go for cobalt radiation. Okay, so these things you need to take care, but this is very selected sample, not for all the samples. uh, Copper works for most of the material, so you don't have to worry about copper. Okay, so then you, for having good analysis, you should also take care of the signal to noise ratio. So what is the meaning of signal to noise ratio? So you can see here there are two spectrum of the same sample. The first one is just a very quick scan, maybe for 10 minutes or 15 minutes. So if you see here, you have a lot of scattering of your X-ray diffraction. And if I increase the time of your collection, data collection, then what happens? This scattering would go off, and you can see, you can clearly start seeing the uh, two peaks properly. Okay, or the splitting of peaks properly. So this is what we call as a good data. Good data should have less noise. Okay, so better signal. So signal should be more compared to the noise. So these things you need to take care when you are collecting data. If I want to do an analysis on this red data, it would be very difficult because you may not be able to clearly distinguish the peaks and the background. So that is one thing that you need to take care. So how to take care of, and also the next one is the solar slits. Solar slits are, you can see here, these are nothing but these are very small thin copper layers or copper films which are stacked one above other. Okay, with different distance between two lines. Okay, so now if you see here, there is something like 5 degree. 5 degree means the distance is more. 2.5 degree means the distance is lesser, and zero point 0.5 means the distance is much lesser. Okay, so these are the this is something like what we call as solar slits. But normally in case of your lab X-rays, it will be mostly fixed, so you don't have to play with this solar slits. You need to just take care of the collection time, data collection time, and also the previous slits, what we see here. Okay, so this anti-scattering, divergent, and receiving slits. So these things you need to take care. But I'm just giving an just example here. So for if you want to do a very good analysis, in that case, what you what you need to have is very good X-ray data. Okay. So what is this good? What is the meaning of X-ray data? should have a high intensity, you should have a better resolution. Resolution in a sense, you should be able to see the peaks properly. Okay. For example, in this case, you are not able to see. You may think this is a single peak. Okay. But if you do a very good data collection, then what happens? You can see this is from two different peaks. Okay. So that is the meaning of better resolution, good signal to noise ratio, what we talked here in this case, and then complete diffraction spectrum. So in case of inorganic, if you are having inorganic samples, like if you are working on some oxides, then you take data at high angles. So normally your most of your inorganic samples, it will start after 10 degree. So you don't have to take the data less than 10 degree, but you need to take up to maybe like 90 or 120, depending on the your X-ray diffractometer. Okay, if your X-ray machine can go up to 120, you can go up to 120. If not, maybe up to 100 or 80 would be good enough. Okay, but you should take very good data if you want to do really good ritual refinement or good analysis. And when it comes to organic, so organic normally they will have uh, large unit cells. So in the sense, you will have the peaks would be in the low angle. So in that case, you should collect the data at low angle, like from maybe the lowest possible. In some diffractometers, they can go from 0.5 degree up to 35 degree, or maybe from 2 degree to 35 degree. So it again depends on your diffractometer. So these things you need to take care in case of your data collection. Okay. So I think I will stop at this point. So then if I have some questions, I will take the questions before going for a short break. Okay. So if there is any question, you can put on the chat box. Okay. So I think is there any chance materials? So in case of your lab X-rays, the energy of this X-ray is not that much. So normally normally in case of your lab X-ray, they are very low energy X-rays. So you may not change the phase, but there is possibility, like if you are having an organic sample, like which is sensitive for radiation, then you may destroy the sample. Other than that, X-ray diffraction is a non-destructive techniques. That means you can use the sample. You take your sample, do X-ray diffraction on that, and then again you can do different analysis. Maybe if you want to do magnetic measurement on the same sample, you can take the same sample, then you can do the magnetic measurement or some other measurement. Okay. So normally X-ray diffraction is a non-destructive technique, which can be which can be which will not normally destroy, but in some cases, like for organic samples which are sensitive or hydroxide samples, uh, it may slightly make some radiation damage, but again it depends on the sample. So it cannot be generalized, but it is again a sample data. Okay. So next one is so I will pay this later. So can you explain about background? So background again, this it depends on the uh, on your sample. So if it is having very good diffraction, then you can take less time. Even in 15-20 minutes, you can get very good diffraction. But if your sample is having a lot of fluorescence, which is your next question. So if it is having a fluorescence, so in this case, how to avoid extra fluorescence is you have to put some filters. Okay. So normally what happens is in most of the X-ray X-rays, they put this what we call as mask before sample diffraction. Okay. So you can also place this mask after your diffraction. So that is one way to avoid your fluorescence. So this you have to ask your technician who is collecting the X-ray diffraction data for you. So okay, so he can actually place this mask after your diffracted. Okay, so you can put it part, then you can avoid this X-ray fluorescence. That is one way of using it, because you cannot change your X-ray tubes, because it's not a easy task. And also yeah, copper X-ray is economical one. Not, but if you want to change to cobalt, it will be more costlier. Okay, cobalt X-ray tube would be more costlier compared to copper X-ray tube. So you cannot change your X-ray tube very easily until unless you have option to do it. So one way to do it is you can place this mask in the diffracted part. Okay, so in that case, what happens? Your fluorescence would be avoided to some extent, but again, you should take care that the intensity will come down. The intensity will come down, so you have to collect for longer time. Okay, so that is one thing. Then, what are the possible reasons for broad peaks that are usually obtained in XRD? So this broadening can be due to your sample. For example, if you are doing, for example, in this case, if you are having a nanoparticle, then the broadening can come to due to the size effect. Again, this I will explain in stress and strain. I am going to cover it again in the later sessions. So, and one thing what you can do is you can take high crystalline sample. Normally, you will have a silicon powder which will come along with your powder X-ray diffractometer. So you take this X-ray, you take this silicon powder, or you can what you can do, you can take any like cerium oxide or silicon oxide. You heat it at very high temperature, like maybe around 1200, 1400. Uh, so then what you can do, you can collect data on that. Okay, so that would give a better idea. So this again, I'm going to show this in some of the examples. Okay, so this peak broadening can be even due to sample or due to your settings. Okay, so if in case if you're using uh, wait just so if I use this big slits, then what happens? For the sample, you get broad peaks. If I change this slits, if I keep decreasing the slit size, then what happens? The peak broadening is going to narrow. So it is going to get narrow. So this you need to be you should take care, because this broadening of peaks can be due to your sample or due to the instrument. So this we will again discuss later in detail. Okay, when we uh, uh, go for analysis. So as explained, 0.05 step is preferred with the greater data over time collection. Are these two parameters related to each other or independent? So these are independent. So why I will tell you, the reason is, if you are having a high symmetry in the sense, if you are working on cubic crystals, or if you are working on tetragonal, or even in case of orthorhombic, you can use 0.05 step is good. But if you are having a monoclinic structure, and in that case what happens, your peaks would be very close to each other. So in that case, it will be very difficult to distinguish if you don't have a very proper step size. Okay, so if you decrease the step size, then you can decrease the step size for a lower symmetry like monoclinic, where you will have peaks very close to each other. For example, this blue line, what you see, it has peaks very close to each other. But in case of next example, so for example, in this case, the peaks are already well separated. So in this case, you don't have to go for smaller steps. Instead of that, you can collect for longer time. Okay. So these two are independent. It depends on your sample. So you need to know the sample history that we will go to study later. Okay. We are going to again discuss those things in later stage. Okay. So if you have any more questions, you can ask. You can unmute yourself. You can ask. Then we will take a short break before going into the next part of the talk. So what I'm going to do is I'm going to stop this recording because easy because